So the philosophy of compactness is if you have a set that you know is compact, and you can find a bunch of open conditions that cover up the set, whatever that means, you can restrict it using only finitely many of them. And once you have only finitely many things, if there's like a number that parameterizes them, you can pick the biggest value for those numbers or the smallest value. You can do anything you can do with finite sets. So compact is like the analog of finite sets in the context of real analysis. So let's try to prove the Bolzano, the nested intervals theorem. Maybe I'll let you choose Bolzano-Weierstrass or nested intervals. Which would you rather see discussed? Bolzano-Weierstrass? Oh yeah, I had that extra bit of time because I didn't go through the proof of finding profile. That's right. People feel okay about using compactness to do stuff like that? We'll see some more examples of like the extreme value theorem. One of the options will be use compactness, and maybe we'll talk about it again then. Well then, let's then start in on functions. Let's talk about continuity and limits of functions. So, we've done things for sequences. Let's do something that is going to, I think, feel very satisfying if you think of this class as like, what are the underpinnings for calculus? Continuity and limits are important for calculus. And let's start with something that you should remember from Calc 1. Tell me, if you have a subset of R and a function defined on that set, and numbers p and l, what does it mean to say the limit as x approaches p of f of x is equal to l? What's the definition of that? Anyone just remember? Let's try to like reinvent it on the spot. Yeah?
Let's start with a for all epsilon greater than 0.
There's probably a for all epsilon bigger than 0. And in fact, if you know it should begin with a for all epsilon bigger than 0, and you want the limit of f of x to be L, how do you think it should end?
The absolute value of p minus L is less than epsilon.
Not quite. And I think this will become very clear if we start with what's the definition of the limit of a function. So let's start with that. Note the limit of the sequence. What's the definition of that? I'll start with this.
There's this little n for n such that little n is greater than n. And then the absolute value of a of n minus L is less than epsilon.
So let's parse this out in terms of what each bit is trying to say. So this epsilon is like, no matter how close you want an to be to the limit. Right, that's the job of epsilon. It's like how close is an to the limiting value? An, you can make it that close. But it's not that close for every n. All that stuff says is as soon as that little n is big enough, a sub n is that close. So think about, like, in terms of this sort of language, what this means. So instead of an being close to L, we want f of x to be close to L. So no matter how close you want f of x to be to L, f of x is that close. So I think the very last clause in the definition of the limit should be, let's give myself 2 lines. I think there's the final thing that's written in the definition of the limit. What does that as x goes to p mean? So it's like, instead of caring about what happens when little n is really, really big, in that definition, what do we care about? Yeah.
Maybe the percent is p minus something, that's something that's really, really small.
Yeah. Yeah. As long as the difference between x and p is small, something good should happen. Nice. We feel good? Let's put that up. So, well, I believe epsilon bigger than 0, so that epsilon is supposed to be like a really small number. There should be another really small number. And I don't know. What letter should I use for this number? In this case, there is an answer that I'm fishing for. Yeah, how about a delta? Not because it's like the only choice, but because it's the one that you should maybe be like triggering memories from calculus. For every epsilon bigger than 0, there exists a delta bigger than 0, such that for every x in the domain of this function is called u, and I'm going to like be plugging that x into the functions that better be in the domain. If absolute value of x minus p is smaller than that small number. And I'm giving myself space here because there's another thing I'm going to add. And the distance from f of x to L is less than epsilon. And there's only one thing that I'm going to add here for a slightly technical reason. I'm going to write a 0 is less than. And if you like, here's why. Does the limit as x approaches p, like is that thing supposed to care what happens when you plug in x equals p? No, so we should use the if part of the if then to say we don't care what happens when x equals p. And this 0 is less than does that job. All right? There's a definition. Let's put it down. Let u be a subset of R, and f from u to R be a function, let p and L be real numbers, then the limit as x approaches p of f of x is equal to L means for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in the domain of the function, if 0 is less than absolute value of x minus p is less than delta, then absolute value of f of x minus L is less than epsilon. Now that the definition's written down, does that like maybe spark some memories? I hope so, but like, I get that it's like something that happens early in the semester in Calc 1, and it's like the most technical thing for a while, so I think a lot of people like lose it. But now it doesn't seem so technical compared to other stuff, right? Like, that seems like a perfectly reasonable definition. And hopefully, like, this explanation of comparing with definition of the limit of a sequence helps. I think I might ask this as a pop quiz, maybe on Friday. I think it seems like something that I should do. Hopefully I remember. Let's use that to prove a thing. Let's suppose I ask you to prove that the limit as x approaches 3 of 2 minus 4x is, what should that limit be?
like, forget that this is a class of analysis. Like, in like Calc 1, what would you tell me that limit is? Right here, a negative 10. Let us prove.
All right, so that red thing is the technical statement I want to prove. So what's the first line I should have? Consider any epsilon bigger than 0. And the next thing I need to do is set delta to something. And just like big N, maybe I don't know what that delta should be yet. Hopefully it's not too hard to find. What's the next line I should have? So I guess it's not clear like what the set U is. U is the domain of the function. What's the domain of that function? Yeah, real numbers. When like you see a formula for a function and I don't specify a domain, the domain's just as big as it can be. It's everything for which that formula makes sense. So I need to prove something is true for every x in the real number. So what should my next line be? Okay. What's the next line I should have?
Assume exceptionality.
Yeah.
So U is less than. So x minus 3 is less than delta.
Yeah. I want to prove an if then, so you get to assume the part in the if. And now I guess I need to prove the then. Then absolute value of 2 minus 4x minus the thing that you think the limit is, negative 10. I'd like that to be less than epsilon. And like, it's always dangerous to do what I'm about to do. I'm about to just hope that I can come up with the right choice of delta while I'm writing the proof. Really what I should be doing is like going to scratch more paper and like doing it there, but this seems simple enough that probably it'll walk out okay. All right, you're not living on the edge, you're taking up too much space. So I guess let's try to simplify that until we can like see how to take advantage of this assumption somehow. So, what's that simplify to? Either many steps or like little steps. Cool. And the assumption we have has something to do with an x minus 3. Can you get an x minus 3 to show up out of that? Yeah. Tell me how. Flip them, factor out of 4. So, factor out of 4 and write them in the opposite order of x minus 3. Is that what you meant? Okay. All right. Cool. Now how can I take advantage of this assumption? That seems sensible. And let's see. So that's what I have. I have this difference is less than 4 delta. I would like that difference to be less than epsilon. That seems like a good choice of delta.
1/4 of epsilon. Does that choice of delta result in 4 delta equals epsilon?
Nice. And I guess there's definitely one thing that's left out of this written argument. Like, there were wants that went along with that string of inequalities and stuff.
Maybe I'll include them. Then this happens by simplifying. I'm not going to correct that spelling. Simplifying. Factoring out a 4. And since delta equals epsilon over 4. And now I guess let's just see if that does the job. Does this argument start by considering any epsilon bigger than 0? Does it then come up with a choice of delta? Does it then consider any x in the domain satisfying the inequality we want in the if part of the if then? And then we conclude the then? Cool. Yeah, there's a proof of that of a limit. And that's like the most complicated limit argument that you probably do on your own in Calc 1. There are other ones that are done on the wall and stuff. So there's the definition of the limit now. There's a constraint on when a limit even makes sense to talk about. In that I'm going to underline this. So what if there are no x's that satisfy that inequality in the set U? That would be like that, right? In that would mean that the if part of the if then is false, so the whole if then is automatically true. So that's like bad. That means that if you don't satisfy the hypothesis of that if then the limit can be anything you want, which is like weird. You would conclude that the limit is equal to 5 and 7 and 23. So we'll just forbid that. We'll only take limits at limit points. Do you remember the definition of a limit point?
Very similar to the
Yeah. It's no matter how small a delta we pick, we can find an x in the set that satisfies the inequality. Oh, so if you add a limit point like this is never vacuous. That's good. For a subset U and a point P in R, P is a limit point if, no matter how small a delta you pick, there exists an x in U with 0 less than absolute value x minus P is less than delta. Right. If a point is in a set but is not a limit point to that set, I will call it an isolated point. Does that seem like a fair thing to call such a thing? Yeah, it's like in the set, but as long as you look in the little delta neighborhood, you don't see anything else in the set nearby. It's got no points nearby. So, let's draw that. So a point is isolated if P is in U and P is not a limit point. Well, I'm going to do the I'll write down the not and the definition of the limit point, and then put the result of pushing the not through, doing logical calculus on the next line. So if it is not the case that for every delta bigger than 0, there exists an x in U with 0 less than absolute value of x minus P less than delta. So a point is isolated if, what happens when you negate that?
It exists a delta greater than 0, such that for all x in the domain,
let's see. Whenever you see two inequalities written like this, like they're joined with an and. And when you negate an and, you get an or. So I'm going to do something off to the side. So let's negate this. This is going to become either 0 equals absolute x minus p, or absolute x minus p is bigger than or equal to delta. Uh, 0 equals absolute value x minus p. What does that mean? X equals p. So for there exists a delta, so that for everything in the set U, either that thing is equal to p, or the distance from x to p is bigger than delta. And I think instead of writing that as an or, I'll say, well, x in U minus p, absolute value of x minus p is bigger than or equal to delta. Does that accomplish the same result? Cool. There's a definition of an isolated point. An isolated point is a point so that as long as you look like really close to that point, you don't see anything else in the set other than that point. Finally, continuity. This is another thing you should maybe remember from Calc 1. And maybe you should especially remember it because the definition of the limit is written right above. What does it mean to say a function is continuous at a point? Well, maybe I'll start you with this. So think about what continuity means. A function is continuous at a point if, as long as I pick another input that's close to that point, the outputs are close. So instead of concluding that after x minus L is less than epsilon, I think it'll be after x minus F of p. And that happens as long as the input x is pretty close to the input p. So I think a bunch of this setup is still just almost the same. There exists a delta bigger than 0, such that for all x in U, if absolute value of x minus p is less than delta, then absolute value of x minus f of p is less than epsilon. Hopefully now that that's written, that also maybe strikes some memory bells in terms of what continuity means. Great. So, let's just make some observations. Continuity versus limit. Those two definitions look pretty close, right? Let's make observations about things that are or are not different. Continuity, you can only ask about continuity at a point if f of that point is defined. That makes sense, right? You can't be continuous at a point if you can't even evaluate at that point. Are you allowed to take a limit at a point that's not in the domain? I mean, you better be able to, because that's the whole point of limits, right? The definition of the derivative is oh, I can't actually plug in h equals 0, or else I divide by 0. I need to plug in h equals almost 0. So you sure better be able to check the limit of things not in the domain. But as we discussed, you better have it better be a limit point that you're checking at. Otherwise, the definition of the limit and the definition of continuity look pretty similar. And there are connections between them that we will explore. How do people feel? Any questions right now? All right. Let's. Oh, one more thing. That's what it means to be continuous at a point. If you have a function that's defined on some set, what should it mean to be continuous on that whole set? Just like continuous at every input in that set? So a function is continuous on a set U if for all p in U, f is continuous at p. That seems like a reasonable thing to be the definition. And as is our habit, that thing that I just parenthesized in red, is that a what? Parentheses? No, it's not. Could we expand out that definition more to get like a fully quantified thing? Which is useful whenever you want to prove something. So, what does that mean? That means for all p in the domain U, and for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in the domain U, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. Did I do that correctly? Cool. Maybe put these parentheses there so you can see the connection from one line to the next.
Cool. So, there's the formal definition of continuity on a set. Let's prove that a thing is continuous. There's an example of a thing that I think is probably continuous. A linear function. Think we could come up with a proof? I hope so.
Let's go through the first couple lines. So the domain of this function is just the whole real line. You know what, let's not check for continuity at one. Let's just check if it's continuous. So I'm changing the deal. Pray I do not change it all. Prove that f of x equals to 3 minus 2x is continuous on R. So if that's what I want to prove, then by looking at the line above, how should I start? I want to prove something for every p in the real numbers. So I guess I better start by considering any p in the real numbers. And just in order to use varied language, let's let p be a real number. What's the next thing I need to declare? Epsilon. Also universally quantified? Let's let p be a real number, and let's let epsilon be bigger than 0. What's the next thing I need to do? Set delta to something. Anyone have a guess already? Cool. Some function of epsilon. So notice it could also depend on p. It can depend on any variable that's already defined. So I don't think it will have to, but sometimes it will need to. I think this example is simple enough that it might not. So anything that depends on p or epsilon.
That's always true for any universal variables, right?
Yeah. So whenever you have a like a formally defined thing for any p, for any epsilon, there exists a delta. That delta can depend on anything that comes previous, but not on anything that comes after. This n can depend on epsilon, but big N sure as hell better not depend on little n. Because then I could take big N to be little n plus 1, and then the if is false, and so everything is true, which is like bad. Awesome. So let's let delta be something that we get to pick. guess we need to let x be a real number. We get to assume the if part of the if then. And now, what is it that we want to show?
Fx minus fp, absolute value less than epsilon.
Absolute value of f of x minus f of p less than epsilon, and we have a formula for f of x. So let's use that. Then, absolute value of f of x minus f of p, I would really like that to be less than epsilon. Then let's use the formula for f. Do I know what f of x is? 3x minus 2. I'm going to include possibly excessive parentheses. And you've played this sorted game enough that I don't think I'm worried about you leaving out those important parentheses. How's that simplify? 3x minus 3p. Let's factor out that 3. I think I do want. Okay, what next?
Delta should be epsilon over 3.
Let's try it out because we can use that now. If delta is equal to epsilon over 3, is 3 delta equal to epsilon? Awesome. And now I guess like a concluding sentence. Thus, f is continuous on all of the real numbers. Nice. Cool. So, continuity and limits, those two definitions seem pretty closely related. And did this proof of continuity feel an awful lot like the proof of the limiting statement? Like, it would have been the exact same work if I asked you to prove that the limit as x approaches p of this function is the same thing as f of p. And indeed, this theorem says that those two things are closely related. Let u be a subset of R, let f be an element of u. I'm going to cover up that bit. Then f is continuous at a point p if and only if the limit as x approaches p of f of x is equal to f of p. And the two sentences, the things in between, are p had better be in the domain and be a limit point of the domain. The reason for that is because when can you talk about limits? You can talk about limits at limit points. If you try to take a limit at a place that's not a limit point, you can make sense of the definition, but the definition will tell you that the limit is equal to everything, which is dumb. So don't do that. Only try to take limits at limit points. Given a function, you can only ask about continuity at points in U. So if P is in U, so you can ask about continuity, and is a limit point of U, so you can ask about the limit, then continuity is detected by limits. And by looking at the clock, I think I want to do one of the implications, but not the other, unless people really want. So let's prioritize one over. Well, I guess start with the setup. Let U be a subset of R, F be a function defined on U, P be a point in U, and P be a limit point in U. There are all of the assumptions. Now I have an if and only if to prove. Should I do continuity implies or limit implies? People have a preference for continuity implies? People have a preference for limit implies? Okay, then we'll do the first one, and then we'll see if people feel like it should go the same. So, let's suppose that f is continuous at p. I need to prove this limit statement. And I know the structure that the proof needs to follow. I need to consider any epsilon bigger than 0. Consider any epsilon bigger than 0. I need to come up with a choice of delta. And I know I'm not going to be able to get an explicit choice of delta. Like I can't get a formula for delta because I don't know a formula for the function. Instead, I need to use the assumptions to get a choice of delta. Well, I know this function is continuous in E. Does that give me a delta? I think so. I know that for every epsilon bigger than 0, there is a choice of delta. Do I have a positive epsilon chosen right now? Let's use that. Since f is continuous at P by assumption, we get that there is some delta bigger than 0, such that for all x in U, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. Do you agree? That's just the definition of continuity. And I assumed continuity, so I do get that. So, for any epsilon bigger than 0, I come up with a candidate choice of delta. And hopefully it's the right choice of delta. If it's not, maybe I need to divide some stuff by 2. Now I should consider any x in U which satisfies this inequality. Because I want to prove something about the limit. We feel good? Let's remember the goal. So the goal now is going to be that. You get to assume this. You want to show that where L is equal to f of p, because I want to show the limit is equal to f. All right, well, let's try to do that. There's an if-then that has as its then exactly what I want. So if I can get the if to be satisfied, then I win. Do I have the if satisfied? Oh, yeah, great. Let's just write that down. In fact, I have more than the if satisfied. I also know that it's bigger than 0. So in particular, absolute value of x minus p is less than delta. So I can now use this line. Since absolute value of x minus p is less than delta, it follows that all right. So let's just see if we're done. Have we shown something for every epsilon bigger than 0? Did the thing we do involve concluding that there exists a delta? Yep, we used continuity to get that delta. We then considered any x in the domain U, I hope. Yeah, that's it right there. We assumed absolute value of x minus p is less than delta and bigger than 0, and concluded that absolute value of f of x minus f of p is less than epsilon. Hey, cool. That's a proof of the limit. Do you think the other direction will be close to the same? Yeah, I think it'll be basically verbatim with basically those two swamped. So I think it'll be like the same proof again. Should we do the other direction? Is that, you think, walk last time? Yeah.
I guess one of the questions is how would you get a greater than 0 from x minus p?
I think the best answer to that question is let's try to power through the proof and get to that point and then slow down. So let us prove.
And I think the strategy I have in mind is something case-wise. So, let's suppose this limit is equal to p. Let's consider any epsilon bigger than 0. We'll use the definition of the limit to get a delta. And I think I accidentally left out that line. So that was like fast, but I think I just copied down the definition of the limit after the halal epsilon. So now I need to consider any x in u, such that the assumptions about continuity So here's how I will propose. If I also had that 0 is less than, then I win. So let's just make that one of the cases. On the one hand, we might have or if the absolute value, or it might be that absolute value of x minus p is equal to 0. Are those the only options? And so, like, that was fast, and now we're at this point. And there's like an either-or situation. Let's walk in cases. In case 1, why did you win?
We have the A part because that's the implies that
Yeah, let's maybe label this with a star, since I'm going to point to it, by star, since 0 is less than absolute value of x minus p is less than delta, absolute value of f of x minus f of p is less than epsilon, and what have you. In the second case, absolute value of x minus p equals 0. What's the only way absolute value of x minus p could be equal to 0? X equals p? Agree? So, x equals p. I think I can fit this all out all the way. Now let's look at what I want to analyze. I would like f of x minus f of p to be small. Is it? Yeah, right? It's a function. If x equals p, then f of x equals f of p. Oh, so do I still win? Yeah, so like, you do need to worry about it, but the only difference is what happens when x is equal to p, and when x is equal to p, x is equal to p. Groovy. Alright, so the thing we just proved is as long as you're at a place where both limits and continuity make sense, they're the same thing. Let's check the type of place where continuity makes sense but limits don't. So let's suppose that u is a subset of R, is a function from u to R, and p is in u and is isolated. So there's nothing in the domain of the function that's close to p other than p itself. This claim says that continuity is a silly thing to talk about because everything is continuous. And let's try to prove. And maybe we'll see if that intuitively makes sense. So continuity says that you need to check every input that's close to p and see if the outputs are the same. Isolated points are points where there are no inputs close to p. So that means there's nothing to check. So yeah, it should be true. Let's cook up the proof, and let's follow the recipe. Let's consider any epsilon bigger than 0. I now need to come up with a choice of delta. The only assumption I have is that P is isolated. What's the definition of an isolated point? Well, let's flip back. There exists a delta. Oh, that's good. I want to come up with a delta such that for all x in U minus P, the difference between x and P is bigger than or equal to delta. There exists a delta bigger than 0 such that for all x in U minus P, absolute value of x minus P is bigger than or equal to delta.
So far, so good? And now I know what I need to assume next.
I need to assume x is in the domain U, and absolute value of x minus P is less than delta. Oh, so let's check out what that means in light of this statement. So absolute value of x minus P is not bigger than or equal to delta. So x cannot possibly be in U set minus P. Oh, so x only has one choice, right? It's in U, but it's not in U take away P. It must be that x equals P. So, is the absolute value of f of x minus f of P less than epsilon? Yeah, because what's it equal to? Wait. That seemed pretty good. And I have 4 minutes. I think that's enough time to do the following, because I'm not going to prove much of anything more. I'm going to state some more things and make a corollary observation. So we proved a bunch of algebraic limit laws for sequences. They all still hold for limits of functions. If you have a constant function, what's the limit of that constant function? If you take the identity function, f of x equals x, what's the limit as x approaches p of x? I bet it's p. Right, this isn't a proof, but if x gets close to p, then x gets close to p. If f of x gets close to L and g of x gets close to n, then what does f of x plus g of x get close to? Same thing, but the minus. And multiply. And divide by as long as you don't divide by 0. Nice. And I'm not going to prove these. Instead, here's what I'm going to say. Do you remember when we proved those for sequences? The proof is almost exactly the same, except anything involving an n becomes something involving a delta. That's all. And you will prove one of them by using that philosophy. And as a consequence, let's put these things together to notice that we have continuity results for, we have algebraic limit laws, we have algebraic continuity laws. And let's just prove one of them. They all have exactly the same proof. There's not going to be any epsilons or deltas. It's going to be assembling the results we already have. So let's prove that the result of dividing continuous functions by each other is continuous as long as you don't divide by 0. So let's start with this. If P is an isolated point, what do you know about functions on isolated points of the domain? They're always continuous. And that's hopefully what 7.1.5 is. It is. All right. On the other hand, P is a limit point of view. I know that continuity is the same as limits for limit points. So, since f and g are continuous, theorem 7.1.4 says that f of p is equal to the limit x approaches p f of x. G of p is equal to the limit as x approaches p of g of x. On the other hand, this theorem before that we hadn't proven tells us how to take the limit of a quotient. So the limit f of x divided by g of x is equal to the limit of f of x divided by the limit of g of x. Oh, wait, but do I already know what the limit of f of x is? It's f of p, right? Does this say that the limit is the same thing as plugging in p? So the reverse direction of theorem 7.1.4 says f divided by g is continuous at p. And here's something that I assert with no time left. All of those claims now have exactly the same proof. So here's something that isn't homework, but I want you to do nonetheless. Look at the next page. Does that look like a bunch of the same blanks? Yeah. Fill in that diagram to prove, I guess this wants you to do multiplication, but just pick one. Prove one of those things using this limit translation. Cool. All right. So, that got a little bit fast close to the end. But here's the thing hopefully nothing today felt fancy. And you should be packing at this point. I'm out of time. It should all hopefully have felt like stuff that felt a lot like what we were doing with limits of sequences anyway. So the game is like all the same techniques you know to prove things about limits of sequences. Those techniques still belong. You just need to come up with a delta instead of a big N. And if you can remember that bit of philosophy, then you can prove lots of things about limits of functions. In particular, you can prove everything in the homework. Yeah.
So I'll be on Friday and Jake will be on the daily.
Yeah, that's right. You told me that. I appreciate throwing my name. Thank you.
So this classroom, I looked at their,
They put a bunch of stickers up outside of every classroom saying where the lost and found is. That's where, well, was it? It might be somewhere hidden up here.
classes, their lessons, yeah, I might have also just moved around when I was switching cars, so it could be there too, but I forget.
Yeah, there's like lost and found instructions on a piece of paper right there. Student lost his glasses.
Oh my gosh. Yeah, I had a student lose her glasses in one semester and she could still play lacrosse, but she couldn't see what she did.